Okay, good afternoon, everybody. My name is Tom Pollard. I'm a biology professor and dean of the graduate school, and I'd like to welcome you to the fourth of our Company of Scholars lectures here at the graduate school for this year. This is a series of public lectures meant to expose the scholarship of our faculty here at Yale to a wider audience. And in that regard, we've had three very interesting lectures so far on completely different topics. The first one by Jacob Hacker had to do with public policy and wealth distribution in the United States. The second by Beverly Gage had to do with J. Edgar Hoover and the foundation of the conservative movement in the United States. The third one by Katie Lofton had to do with the impact of religion on parenting in the United States. So we have sort of a theme of connection between our academic work and the public for our lecture series this year. And I selected my friend Paul Tipton over here to give this lecture because he wrote a very thoughtful op-ed piece in the LA Times that was distributed to other newspapers by the LA Times on why the investment made by the public around the world through their taxes in this big physics experiment was worthwhile. So his topic today is finding the Higgs boson, what our taxes taught us about mass. So let me tell you about Paul. He can take the floor in a moment. He has his doctoral degree from the University of Rochester and then went off to UC Berkeley and to the Fermi Lab in Illinois for postdoctoral work, returned to Rochester, rose through the faculty to full professor in 2000 and 2006. We lured him here to Yale. He's now serving as the Director of Graduate Studies in the Physics Department, and on July 1st, he will be the next Chair of Physics here at Yale. So thank you very much for joining us here today, Paul. And thank you all for coming.
Thank you very much. So it is my pleasure to bring news of a momentous discovery in physics. And I'm sure you've heard about the Higgs. Almost everyone, you'd have to really be hiding under a rock or something to not hear anything about the Higgs. So what I'm going to try to do is give a talk that complements what I hope and think you probably already know. I want to start by thanking my colleagues both around the world on the Atlas Experiment, of which I'm a member, but also my colleagues here at Yale, Tobias Galling, Sarah, Vitek, and Keith Baker, and also the physics librarian, Kaylee, and Catherine James, who is from the Beinecke. Let me start out with a bit of a warning. So in physics, the big three are space, time, and mass. And as Kramers alludes to, any very important fundamental entity is going to be hard to attach a well-established meaning to. And so that's a bit of a warning. I'm going to try to do that, to define and understand mass at a deep level. A more succinct way of saying that is that mass is a mess. And Wendy said this in the context of inertial mass versus gravitational mass and the lack of a clear non-circular definition, but it leads to the same idea. So an outline for today is I'm going to give a rather lengthy introduction on the history of mass and how the Higgs relates to that. And then I'll talk about the Higgs search and how we produce and detect the Higgs boson, or what we think is the Higgs boson, what's next at the LHC, and then lessons beyond science, as Tom alluded to, funding, ethics, internationalism, and taxes. So it's going to be a big introduction and a big conclusion with a very little sandwich of the Higgs search in between. Okay, so a brief history of mass. So, and at the end, I'm going to give lots of opinions, and they're my opinions, and I apologize in advance if I offend anybody, but I'm going to give them anyways. So, and speaking of offending, I'm going to start the history of mass skipping over the ancients who gave us the theory of the atom, and start right away with Newton, who gave us a theory of mass that we could do something with, a quantitative theory with predictive power. Newton in Principia, the most important of his works and arguably the most important document in science to date, on the first page of the first book of Principia, he tried to define mass. And he did so it's in Latin, of course. So it's quantitas materiae, which is matter, and one would translate what comes next as matter arising from its density and volume conjointly. So the problem with Principia is that it's in Latin for the first, that's the one problem. The second problem is that it's basically math, but it's written in words. So he didn't basically have the algebraic tools we have, and so when you read it, it's like he's playing charades. I'm thinking of an equation, and he, so in paragraph form, so to translate this into math, which I believe what he was trying to say is that mass is density times volume. That's what most people think he meant by that sentence, which is a bit problematic because density is mass over volume, and so we basically just go around in a circle. And our confusion about mass, I think, can be traced back to this beginnings where Newton stumbled over to himself. Now, Newton then went on to, with putting aside this circular definition, he used mass to get us F equals ma, and m being the sort of the charge of the gravitational force. And operationally, we now can define mass, right? Mass is our ability to resist acceleration because F equals ma. If you've got a big mass, you can have, for a certain applied force, your acceleration will be less. And similarly in the gravitational equation. So you can get somewhere with a circular definition, it turns out. So, so we owe to Newton a bit of our confusion. Now, let me see. Okay, so it turns out that this story has a bit of a local connection. These newspapers like to sell local connections, so I'm doing that now. It turns out in 1713, there was an agent for the colony of Connecticut in London, and his name was Jeremiah Dummer, and his job, among other things, was to gather books for a library for a new struggling college in Connecticut. And he went calling on the head of the Royal Society at the time was Isaac Newton, and he asked for some donation of books. And Isaac Newton in 1713 had a new version, second edition of Principia, and he gave Jeremiah Dummer a copy of that and optics and a few other things. And we have here that copy, courtesy of the author. Now, it turns out this is probably the second copy of Principia that made its way across the pond. The first went to the colony of Pennsylvania, and it was bought by James Logan. So they had to buy theirs, and we got ours for free. So that's good. But he read it and devoured it. He went on to become the mayor of Philadelphia, but before on the way of doing that, he taught himself calculus out of Principia, and he devoured it, and he wrote letters about it, and there's scribblings in the margins and everything. It's quite impressive. And I invite you to come and look at this copy and notice how clean it is. So either we're better to books or we ignored this thing for many years, I don't know, but we shouldn't ignore it anymore. So come in and appreciate the fine drawings and great work that it is. Okay, so after Newton, the chemists, Lavoisier and others, through studies of chemical reactions, came to believe that the mass of the initial state of any chemical reaction would equal the mass of the final state, even though the initial state might be carbon and oxygen, and the final state might be CO2. And so that in their language, mass was neither created nor destroyed, which we now know is not completely true, but back then it was a pretty good approximation. The other thing that they came upon was that their view was that mass was inherent, an essential product of an object or a material. And that's because if you had a mole of hydrogen, it weighed a certain number of grams, and if you had a mole of gas and it didn't weigh that, it wasn't hydrogen. And so, mass is an essential feature of each element, and it is viewed as such. Now, to make any more progress on the history of mass, we actually have to step back. It's 1760 or 1780, and we have to start learning about fields. Now, the word field was actually not used until about 1840, but the idea, was in gestation. And we have Faraday was likely the first one to use it in a scientific publication. So in about 1810, it was understood that one could map out in pictures like this one, how a positive charge would be influenced by other charges. And these maps were curious. They would tell you direction, and if you plotted the density of lines, you could actually get magnitude also. So they were very helpful and convenient, but they really weren't viewed as real. But Faraday was a great experimentalist, and he played with gadgets, and he came to believe that in simple electric circuits, energy was taken out of that circuit to set up a magnetic field, and then when you switched off the circuit, the energy would be dumped back into the circuit. And so for a physicist, if something contains energy, like he came to believe the field did, that was surely real. But he never really said it exactly like that, and he worked mostly with magnetic charges, but the same thing could be stated about, with electrical charges, but the same thing could be said about magnetic fields around gravitational fields around masses. So he came to believe that fields contain energy, and it was Maxwell later who showed through beautiful mathematics that light was comprised of oscillating electric and magnetic fields. And since we all believe light is real, it's not hard then to believe that the underlying fields that are contained within it are also real. Now, one might ask, are water waves really real? Maybe it's just the water that's real, meaning maybe it's the vehicle or the medium for a wave that's the real thing. But Einstein came to take the work of Davison and Germer and others Michelson and Morley and others who gave us evidence that there is no medium for light, that light is traveling itself, propagating, and it travels in the vacuum. And so if these fields are independent of any medium, then clearly they're in and of themselves real, and they carry energy. In fact, later on in general relativity, Einstein told us that matter can deform space and time, and in fact, all forms of energy can deform space and time. So fields alter the space they're in, and so clearly they're quite real. So now we can go back to talk about mass, and we're up to about 1910, and we want to talk about the new idea in 1918 or so that de Broglie had that if light is both wave and particle, the particulate nature of light was described in a paper by Einstein in 1905. If light is both wave and particle, maybe the electron and all forms of matter are. And by 1925, that had been experimentally demonstrated. So now quantum mechanics is basically telling us that light is made out of a quantized oscillating field. And in fact, all matter is also quantized oscillating fields, but they're matter fields instead of electric and magnetic fields. So now fields have got to be pretty real because they make up pretty much everything around us. In 1935, Yukawa came up with the idea of how we could actually do calculations with this idea, how we might be able to see how one particle influences another, and that is by exchanging a third particle, which incidentally is also made out of fields, quantized fields. So it was Feynman who told us that electric and magnetic forces on the subatomic level for primary particles are mediated by the exchange of photons. And that was the first of what we would call a quantum field theory. So just on a macroscopic level, just as these people, if they were standing on ice, could exert a repulsive force by exchanging a heavy ball, by each pushing against the ball and accepting momentum from the ball. So on the subatomic level, particles can exchange a third particle and influence each other. So that's the basic idea. Then it was Feynman who made these calculations relatively easy. Anybody who's taken graduate quantum field theory knows they're not easy, but they're relatively easy. And there's just one idea then to get us to where we are today, and that is that in the mid-19th, so Feynman did his work in about 1948. And by 55, people were struggling to try to explain the other forces in terms of field theories, to mimic what Feynman did for electricity and magnetism. But it was Yang and Mills who made a big discovery, and that is that the field of mathematics called group theory has a lot of parallels to the algebra of quantum field theory. And to make further progress, they basically said if you find the right group, that will the rules about how this group behaves will inform the physics. And in fact, if you find the right groups, you'll be instantly able to write down the rules of the physics. And so by 1965 or so, people were able to write down a group that encompassed the known forces except for gravity. And so here's a one-slide summary of what we call the standard model of physics. For those of you who know group theory, that's the group. For those of you who don't, ignore that thing. But basically, that gives us in detail how gluons are exchanged in the nucleus to hold it together, and why the electron that orbits around them is not sucked into the nucleus because it doesn't participate in the strong force. So here are the building blocks of the standard model: the quarks, the 6 purple quarks here, the green leptons, the electron and its sort of heavier companion or sibling, the muon, which decays into the electron, and then the tau, which is even heavier and can decay into the electron of the muon, or in fact, it's got some other options that it can do. And here are the mediators. The photon mediates the electromagnetic force. The gluon mediates the strong force within the nucleus. And then the very heavy W and Z's mediate the weak force. So that's sort of a map. You know, it looks very kludgy and qualitative, but it works in detail, and it's made thousands of predictions to very accurate predictions, precise predictions that appear to be accurate also. So, but there is one last problem, and this problem is that this theory of matter, of how matter organizes itself, wants everything to be massless. And that's actually a problem, and I think it deserves a very big, frowny face. So the problem is, and this can't be swept under the rug. We can't just say, well, you know, the masses are all zero, and we're going to paste a mass in there, because there's certain things that happen, certain symmetries that have to be obeyed that if you give the particles mass, you know, it's very bad. So everything wants to be like the photon, made of fields, but fundamentally having no rest mass. But the idea, the fix, is to propose a ubiquitous field that's everywhere, since massive objects have mass wherever they are. And mass will be generated through an interaction between these massless fields that are the electron or the quark and this ubiquitous field. And dynamically, mass will be generated through that interaction. And if you put that into the theory, it works quite well. And it really, it doesn't look like a kludgy sort of an afterthought, even though it was at some level. So, and the nice thing about this theory is that it has predictive power. It predicts, so that the Higgs works like this. So the Higgs gives mass to objects whether they're moving or not. But the best way to understand it, the best bad example of how the Higgs works is that if the electron moves through the Higgs field sort of like a particle through water, and therefore we interpret it as being very light, but the top quark is very heavy, and it moves through the Higgs field as if it was molasses. And it turns out that this molasses can self-interact and give us the molasses ball, which is the Higgs boson. And it can only do that when it's got enough energy to do that. It doesn't spontaneously make Higgs bosons all over the place. It's got to conserve energy. But it does have this predictive prediction that the Higgs boson should exist. And because the masses of the particles are all wrapped up in this theory, we even know roughly where to look for the Higgs boson. So since I know you're all well educated and have been reading the newspaper, I want to clear up some misconceptions you might have. It was stated in the news last July that the Higgs field is responsible for all the mass in the universe. That is certainly not true. So let's talk about our mass. We're made out of neutrons and protons almost exclusively. And that mass, the mass of the proton, is really not from the Higgs interaction. So the mass of the quarks within the proton are gotten through the interaction with the Higgs. But the proton looks something like this. It looks like 3 quarks that each have the charge of the strong force. So, and it's a very, very powerful charge, so that around it is this intense field, a gluon field. But those gluons are trapped being exchanged in between these quarks. and trap the quarks within the proton, but this huge amount of energy via special relativity is interpreted as mass. So here, equals mc squared is really the E of these fields being interpreted as an m. And that's really what the proton is. Only about 10% comes from the quarks, and most of that is the strange quark that, isn't really one of these three. Okay, so that's that. So now you might ask, the astute listener might ask, how is it that these massless fields can give a massive object? Well, the answer is Einstein said it could, and so therefore it's got to be true. But let me give a better example. Suppose we had a mirrored box and a laser pointer, which we have, and we take two mirrored boxes. So on the inside of these boxes are all mirrors, and there's a little hole. You can't really see that, but there's a little hole right there. So we shine our laser pointer into one of them, and lo and behold, it will get heavier. Now, it turns out if you try this with my laser pointer, it turns out it would take between 100, 500 years to pump enough energy into that box to make it sort of a microgram heavier. So you don't want to try this at home, anyone. But it turns out that people, Jack Harris, who's a very clever experimentalist here, is thinking about ways to do something similar to this, and that is very exciting. So to summarize so far, in 1810, the word field hadn't really been used in physics, but we did sort of map out field lines, and they were a mathematical convenience, but not thought to be real. And by 2013, and of course mass was certainly thought to be real in 1810, but now we think that everything that's real is comprised of fields, so both matter and light. And that mass is dynamically generated. So your mass is generated from instant to instant as quarks are swarming around the proton being emitted and absorbed. As gluons are being emitted and absorbed by the quarks in real time. And all the mysteries of this are sort of swept up into this ubiquitous field that's everywhere. And this is sort of the second time we've had one of these fields that lives everywhere. And many physicists don't really like it, but we're stuck with it. And if this theory is correct, we're correct is it somewhat in quotes because it might be a low energy approximation or something like that. It might be replaced someday, but if it holds together at all, then we ought to find the Higgs boson. So how do we go about finding the Higgs? Well, I've implied that the Higgs is very unstable. It lives about 10 to the minus 25 seconds, which is pretty darn quick. So you can't just go out and dig up half of western Pennsylvania and put it through some machine and sort it and look for Higgs because they're not going to be there. But you can make them if you've got enough energy. So what we do is take counter-rotating beams of protons with very, very high kinetic energy, and we collide them head-on, and that energy then is available to make mass. So again, we're using E to mc squared, taking our kinetic energy and putting it into mass. And that mass can do many things, but one of the things that energy can do many things, but one of the things it can do is make a Higgs boson. The accelerator is the LHC, and here's sort of a schematic representation. So this is the Geneva airport, and this is Geneva, and you can't really see the ring as you fly in because it's about 200 meters underground, but this is what it would look like if you had X-ray vision. So there are 4 big experiments, and Yale is involved in 2 of them, the Atlas experiment on the upper right and the Elise experiment that Helen Keynes and John Harris are involved in. So, and the collision energy at maximum will be 17 TeV, or 7 TeV per beam, 14 TeV for the total, and that's a proton weighs about a GeV. So this is like 14,000 times the energy of a proton. So let's just walk through some of the details. This is an amazing machine, one of the largest machines in the world. It's in a 16-mile tunnel that's underground. It's basically a 16-mile ring of superconducting magnets that are all at about 2 degrees Kelvin. It takes about 96 tons of liquid helium to keep them that way. Here's a picture of one of the last magnet being lowered down in April of 2007 through one of the access shafts. And here's a picture of the final assembled magnets, and you can see the gentle curvature. and the person riding in the tunnel just because he can. Now, the main thing about the LHC is that it's an amazing machine, and we want to use it again and again and again. So we want to make sure that when we put beam in it, we've got an exit strategy for how to get the beam out safely. So that's a big task, because when particles are going very close to the speed of light, you can really they can hold a lot of energy. And so if we have the LHC filled to capacity at design energy, it has the energy, the equivalent kinetic energy of a 747 during takeoff. But that's not the only energy that the LHC is storing. There's a huge amount of energy in the magnetic field that's used to bend the proton's trajectory into this 16-mile circle. And that energy is 747 at cruising speed. So one has to be very careful, and we've tried very hard to take care with this machine. So our first data from the LHC, we have collision data from September 2008, when we first started turning on the thing. And collision data, we call it collision data because we're trying to collide protons with protons. But in fact, this was magnet-magnet collisions because our protection didn't really work. So we ended up having an open between two magnets, and that caused this catastrophic magnetic force that repelled the magnets and bumped them. It was literally a train wreck where magnets are bumping into magnets down the chain. And we ruined about 40 magnets, but it turns out we had about 50 spares. And so after readjusting our protection circuitry, in about 10 months we are underway. And now I think it is safe to describe the LHC as the biggest Swiss watch in the world. It's an amazing machine that functions amazingly well, and we owe a huge debt of gratitude to those who did research and development and prototyping and then built it and operate it, because it's an amazing scientific instrument. So the LHC can provide data that will allow us to see the remnants of the Higgs once it decays. But we have to first understand what it should decay into. Turns out that about 80% of the time it decays into things that blend in with the background, with the other things that these high-energy protons can make when they collide. And so we almost by necessity have to ignore most of what the Higgs decays into. But the largest thing that we're currently actually looking for is looking for it to decay into the heavy companion to the electron called the tau. And Emma Ideal and Sarah Demers are currently looking for the Higgs decaying into tau pairs here at Yale and with colleagues at CERN. Keith Baker is working on trying to see it into pairs of the heavy boson, the Z, and a slightly lighter version of the Z it's what we call off shell because it doesn't quite have enough energy to have its true mass. These are the ZZ star mode is really a gold-plated mode because we'll be able to reconstruct from these four well-measured particles. We'll be able to tell the initial mass of the Higgs. And the last mode only happens, 2 times out of 1,000, but it's to 2 very simple particles, 2 photons, and our energy resolution on photons is very good, and 2 photon events are not that common, so we can, in a very narrow range, hopefully see an excess of if the Higgs is there. So that's our search strategy. Here's a picture of the Atlas Detector that Yale is involved in. When I started in high-energy physics, you could put an experiment in a room, a normal-sized room, and then experiments were sort of the size of a small house, and then they got to be the size of a big house. And this is more like a city block. These are people here, and they're not miniature people. It's a couple 100 million electronic channels. It takes many scientists to prepare those, to prototype them, and bring them into existence, and then operate it. We have about 1,000 graduate students and lots of other things on it. Let's try to briefly explain how it works. We try to learn different things about the particles in different regions. So in the innermost region, we try to let the particles pass through without absorbing them, but sensing them through very thin wafers of silicon, for example. And so we track the particle there. In these regions where we've got calorimeters, we try to absorb the total energy of the particles. And by where, whether early or late, we can learn about the particle's identity. And we can learn about whether it's charged or not by whether it left a track in the tracker. And if particles made it all the way through, left a track, and hits in the outermost layer, we know that that was very likely a muon. And a neutrino escapes our detector, leaving no trace. But we know that momentum had to be conserved. So by everything going to one side, we know the neutrino had to go in the other direction. So that's basically how we do our business. CMS is sort of our rival and companion experiment. It's much smaller, but it's more dense. So there you can see. I don't really have time to talk about this. I know my colleagues at CMS will probably be miffed at me, but nonetheless, we have to move on. So CMS is smaller, but it's more dense. It weighs about 30% more than the Eiffel Tower, so this is the compact detector. Atlas, it turns out, it weighs about 80% of the Eiffel Tower. And had we known that this slide was going to be shown all over the world, I'm sure we could have brought 20% more mass to the problem and exceeded the Eiffel Tower, but that might have been a waste. So the search itself starts with producing the LHC. So the unfortunate news is that we only produce a Higgs 1 every billion interactions. So we're going to be searching for the needle among many haystacks, and it will be hard to find. In the data collected in 2011, we produced about 70,000 Higgs, and you'll know that we can only play around with a few hundred of those. And really extract them. And unfortunately, again, we don't get 10 to the 15 individual interactions. We get about 10 at a time that overlay, and that's problematic. In 2012, we did a little better. We got many more Higgs, but of course, we had 20 interactions per beam crossing as a cost of the higher intensity beam. And as I said, only about 0.2% of all the Higgs produced end up being significantly above background in some mode that we can definitively identify. So here's an example. This is a picture of just the inner part of the Atlas detector. So this is about 20 centimeters across, maybe 25 centimeters across. And each of these planes here is sort of like the focal plane of your digital camera. But it's not really taking an optical image. It's more just looking for a particle to pass through one of the pixels and give a current pulse. And it has to do that every 30 nanoseconds or so. So it's a very fast camera. And this is what we hope to see: H decaying to 2 Zs that then give you something like 4 muons. So here are the 4 muons. And then here are some other tracks that it gave. But it's relatively clean. But unfortunately, what we see is this, where there are 10 other additional events over top it, and these curly circles come about because all this is in a solenoid. So, what we're looking at is proton into the board, proton out of the board. The interaction would be there. And we're sort of looking at a cross-section of what happens as things fly out from that interaction region. Now, we can turn the thing sideways and look sort of along the beam line. And we can see that these vertices separate, and that really helps us clear up this problem because we can identify which tracks go with which vertices. And here we've clearly identified a vertex that has 2 very energetic tracks that come from a Z boson decay. With these sorts of techniques, we can begin to extract Higgs from the background. So we use control samples to a great extent. So this thesis comes from Yale's first PhD on the Atlas experiment, Jennifer Xu. And it shows the reconstruction of the Z boson when it decays into 2 electrons. And the solid line is our computer prediction, given what we know about the physics and Feynman's rules, versus what we observe in the data and the points. And you can see the agreement is quite good. And that gives us confidence that we understand the tracking chamber that was used for this and the calorimeter and our rate of detecting electrons and so on. Now, with much more, oops, I missed something. Something got deleted. Oh, all right. Well, we've collected millions more bigger samples than this, and with it we've been able to access just this tail of the distribution and look at this distribution over 5 orders of magnitude and see that it also agrees. And if our resolution, if our detector resolution wasn't correct, that would not be correct, and so on. So we can really get to the point where we're confident that if the Higgs existed, we would see it. So then we go and look at the data, and these data are from the Atlas experiment in the mode where we're looking just for 2 photons in the event, and of course there'll be lots of other things. And through the clever use of background samples, we can get the shape of what the background should be in the absence of signals, and then we can subtract that off, and that's what we have here. We've got the data points are these data minus this dashed curve, and you can see that that it fits nicely to an experimental, to the prediction of what we'd expect our resolution to be if this object was 125 GeV Higgs. We see in excess of about 440 events in this sample. We expected about a 3 standard deviation effect, and we observed actually a 6 standard deviation effect. So we observed about 80% more Higgs than we expected. But we have uncertainties in our efficiencies and many things that make us less sure that 80% is not a statistical fluctuation. So it'll take more data for us to really understand that. And in fact, with new data, these numbers are coming down to closer to what the standard model is predicting. So in a second independent set of data, we're looking for the Higgs decaying into 4 leptons in the ZZ star mode that Professor Keith Baker's looking at. So this mode is very nice. It's almost self-calibrating. This peak down here at the bottom is the Z decaying to 4 leptons, which it does rarely, but it does do quite frequently and more often than the Higgs. And we can loosen up our selection criteria to get more of them because it's relatively clean. And again, we can compare it to what we expect, and the rate is almost exactly as we expected it to be, and the resolution is quite similar. So that lets us know that if the Higgs is there, we ought to see it. And in fact, if you focus here at 125 GeV, we've got an excess in plus or minus 5 GeV of 125. We see 18 where we expect only 8.3, and that's about a 4 standard deviation effect. Now, our companion experiment, the CMS, sees lovely 2 photon data and also 4 lepton data that's consistent with ours and consistent with a statistical excess at the same mass. And so in terms of statistics, this is not in doubt. We found something new, and that's very exciting. So the question is, are we finished? The first thing, we certainly have discovered a new object, and the question is the standard model complete? Is this a particle that would complete it? And that would charge us to go and measure properties. So if it is the standard model, then Higgs, then we know what it will decay into, and we know certain angular distributions of what those decay products should be, and we can test those against what we expect from the standard model. So far, the indications are that this is consistent with the standard model Higgs. However, we can further and in great detail study what it decays into, at what rates, and how it does that, how it's produced and how it decays, and through what are called quantum fluctuations within the Higgs before it decays, we can probe much higher energies than we can directly. So this is sort of the birth of a new field of physics. And in addition to that, the standard model, as successful as it is, has some rather serious flaws of omission, because it doesn't talk about dark matter or dark energy, which dominate the universe we live in. And it also has some technical problems. It predicts, it has some almost nonsensical calculations within it that lead us to believe that those calculations must be wrong, that some new phenomena must come in and change how we do those calculations. And and those new phenomena would be new particles or new forces, and we believe they're within our experimental reach, hopefully within the reach of the LHC as we go up in energy, but of course that's not guaranteed. So let me first summarize the scientific lessons from what we've learned. We have a relatively complete picture of mass. You know, we're good at hows, but not so good at why, so I put complete in quotes. It's a beautiful picture of mass. It's very elegantly described by quantum mechanics. In 1810, mass was real and fields were math, and now everything is comprised of quantized fields, and mass is not inherent, it's dynamically generated. In fact, it's calculable. If you input the proton mass to QCD calculations, you can get the spectrum of sort of excited states of excited protons, baryons, they're called, in detail, and it's quite exciting. The last piece of the puzzle, the Higgs boson, is really a huge experimental tour de force, and preceding it an incredible intellectual tour de force. The Standard Model does contain flaws, and in addition to using this new thing, the Higgs, as a scientific laboratory, we're hoping to find something new beyond the Higgs. So now we switch from what we know to what I think. An ode to internationalism. So this big science project was done internationally, and in doing so, we avoided everybody having one of these in their own backyard, which certainly avoided duplication of costs. It costs about $10 billion, so you don't want to do this in every backyard. We spread the financial burden as broadly as possible. Almost every taxpayer on the planet had skin in the game. Taxpayers in China, India, everywhere, the US, South America, almost all taxpayers contributed. It helped us develop patterns of international cooperation in a relatively non-controversial site, right? So we're not trying to do a treaty to control global warming or something even more complicated, like maybe trying to cite the Olympics or something. We're just trying to do a science project together, but yet, of course, to do it, we all have to have visas from our countries and so on, and we have to cooperate and so on. So it's a good way for us to intertwine the fates of many countries, and I think we did that because we all wanted this to succeed. And what's really nice is that everybody owned the results, right? This isn't an American result. It's not a Western result. There are, some 100 countries represented in this discovery. So everybody owns it as it should be. So, an ode to taxes. Taxes are what we pay for civilized society. Oliver Wendell Holmes. I think curiosity-driven research is an excellent use of our common resources, which is to say taxes. It allows us to spread out these things that are potentially not very practical. So high energy physics has given, and CERN have given the world many great things, from the World Wide Web to whatever. But if one wanted spin-offs, you wouldn't start by saying, let's find the Higgs boson. I'm sure we'll get a lot of spin-offs that way. You'd spend your money differently. So this is really motivated by curiosity, by the human condition, which is curious about our surroundings, and the beautiful world we live in, which seems appropriate to study. The alternatives to doing this curiosity-based research with taxes is to not do the science at all, which is certainly a possibility, or to try to find corporate sponsors, if that's even possible. But of course, there you're mixing for-profit and not-for-profit entities, and that could get very complicated. It might be how this takes place in the future, but I think that's I think that could be very messy. So then we can ask, has this been worth it? So being a taxpayer, it probably cost you a couple dollars over the last two decades of your tax money to find the Higgs, and I hope you found it worthwhile. So it's cheap compared to the cost of a movie ticket. Think about it that way. And it was spread over 2 decades, so that's good. Now, Robert Feynman, as he was trying to justify Fermilab, which was built in the 70s, said that Fermilab, or high-energy physics, has nothing directly to do with defending our country except to make it worth defending. He was trying to argue that we should build this accelerator lab instead of another defense lab. And I think that's true. This money is worth it because it helps us do what humans like to do. We are innately curious, and if we're busy being curious, we're not killing each other. There's a lot of good things that come out of us being curious. So you could ask about opportunity costs. So given other global needs, can the planet afford this quote-unquote frivolous activity? And this question was raised to me because after the op-ed piece that Tom mentioned, I got some blowback, basically. Many people thought this op-ed was very self-serving, which of course it was. But others said, I got one email in particular that said, I wonder what Professor Tipton would say to the 25,000 parents who lost children due to preventable diseases today. And that, of course, is a very serious question that we have to address. And so after some thought and a glass of wine, I answered the gentleman, and we had a give and take that was actually quite useful. So one way of addressing this is that it's not obvious that poverty and preventable disease are financially limited anyway. It's probably war and corruption that keep that from happening. And many will argue with him, but Jeffrey Sachs says that of order 0.7% of the GDP of the developed world could, and using it wisely, could end poverty. So people can argue with that, but that's a ballpark figure. Now, that should be compared to 4.7% of the GDP we spend on defense and 0.01% that we spend on particle physics research. So if Sachs is right, you could cancel all of high energy physics and you wouldn't do much to help us out of the mess we're in. Okay, so my second to last slide, I just want to spend a minute doing a funny sort of mental exercise. So in my field, we do what are called pseudo-experiments. We simulate samples of data with computer-generated models, and we do this millions of times to try to understand the breadth of possibilities and the statistical nature of what we're about to see. So these are called pseudo-experiments, and I want to imagine running human history a million times as we run our experiments a million times on the computer. So this is something we can't actually do, but it's a Gedanken experiment. It's something that Einstein would have us think about doing. An experiment you can't really do, but you'd like to do. So we've been around for about 200,000 years. So let's try to replay this 200,000 years many, many times, say 1 million times. How often in those million times would we get to develop symbolic culture in a written language? So symbolic culture has probably been around for 100,000 years through maybe ornamental jewelry and things like that probably express something symbolically. To written language, that's probably more like 20,000 years, I think. I hope I have that right. So it's relatively late in our 200,000 years history. It might be that we never would have gotten to it in 200,000 years. Would we reach the Bronze Age? Would we be able to manipulate money? Would we get to indoor plumbing? This is on many people's minds, I think. This is a huge human advancement. Would we get to the scientific method? I note that we've only had the scientific method for 500 of those 200,000 years. So you could well imagine that humans could have been around for 200,000 years and not got to the scientific method, which of course would mean we wouldn't get to special relativity and nuclear power, which is bad, but of course we wouldn't have been able to blow ourselves up, which is good. So it's amazing that we've gotten this far and we haven't blown ourselves up. And then we went further, developed quantum mechanics, quantum field theory, predicted the Higgs, and then we're able to have the affluence and permission of society to go out and spend the billions to bring it about. Now, of course, this is very physics-centric. The mechanical engineer would say that, how often would we get to the development of the wheel, and how often would that lead to the Segway, and so on. But in physics, this is how we look at the world. And I'm really not sort of a Mr. Rogers type. I'm much more like the two grumpy guys in the back of the room in the Muppets, But I do have to say that up with people, right? We got it right this time. It's very self-serving for me to say that what I was involved in is sort of the pinnacle of human society. And believe me, I know that there's a lot of sausage made in high-energy physics. There's a lot of politics and backbiting, and it's not all wonderful. And we certainly express all of the emotions and actions and abilities of human behavior, but we at least helped us to a common goal of this scientific discovery. So to summarize, I don't know why. So beyond the science, so here's to summarize my opinions. The Higgs discovery was quite global. So I don't know why I thought that a scoreboard was an appropriate way to finish this talk, but this is a scoreboard that you might appreciate. So the Higgs discovery was quite global, and that's score 1 for international cooperation and 0 for sort of nationalistic rancor and so on. It was supported by practically every taxpayer on the planet. So score 1 for the glories and virtues of taxation and 0 for hyper-individualism. It was brought about without corporate sponsorship, and so it's the Higgs boson. It's not the Microsoft boson, which, it could have gone that way. So I think that's a good thing. Human curiosity trumped all. We were able to get beyond ourselves and do something that at its root is based in curiosity and not the profit motive or other human activities that are perfectly fine. So strike 1 for human curiosity and 0 for motives lower on Maslow's hierarchy. So what about opportunity cost? Well, 1 for big science and 0 for everything else. For example, eliminating curable diseases. But I think that's a false dichotomy. I don't think that we have to make that choice, and we have enough resources to do it all, or to do at least those two. Thank you very much for your attention.
Okay, I know Paul would be delighted to answer your questions, so please.
Yes, Michel.
So in one of your slides you said non-controversial. Isn't that a bit dangerous? If there is no more controversy in science,
what did I?
Any progress.
In what context? Oh, so Michelle is asking me on one slide I said something was non-controversial. So what I don't remember writing that down.
Well,
I deny it.
I think you said this in relation to the unity of the team. It was teamwork and it was non-controversial.
No, what I meant was that what we were doing was not controversial, like trying to put a treaty on global warming. We were all deciding, we had all signed up to try to find, to do discovery physics at the LHC. So in that sense, it was not controversial. We weren't at odds over our basic premise for why we were in the room at most days. So in that sense, it was not controversial.
But the concepts are still allowed to be controversial.
It was absolutely, many of us, I have to go on record now as saying that I never thought this thing was there. The Higgs just felt too weird. We're going back to the ether, right? This ubiquitous field that's everywhere. I don't like this idea at all, but it's there, and it actually is quite elegant, even though I don't like it. And so, and it's probably true. So yes, I think there were many dissenters in the room, but all of us wanted to know the answer. I think there certainly were biases, and hopefully we put those aside. Yes?
Could you explain again how the Higgs field gives some things mass and not other things?
So the Higgs field gives all elementary particles, the quarks and the leptons, the W and the mediators, the W's and the Z's, but not the photon. It leaves the photon alone. It gives those absolutely fundamental entities their mass.
How does it do that?
So just like in Argo, I can give you our best bad analogy. The best bad analogy is that we move as particles move through this ubiquitous ether, it's like a drag force, and that the drag is proportional to how strongly the particle couples to the Higgs field. And so heavy objects couple strongly, and light objects don't couple strongly and move through it quite well. Now, the flaw in that argument, the flaw in that analogy, is that the Higgs gives mass to objects whether they're moving or not. This is not about resisting acceleration or resisting motion. So it is a flawed argument, but it's the best flawed argument we have. I can pick. Yes?
I have a couple questions. The first one is, so you're saying that moving through the field is what gives objects mass. Is that related to Einstein's theory, or that the faster objects are moving, the more mass they have? Or is that unrelated at all?
So the question is this related to Einstein's ideas about time dilation? Is moving through the Higgs field like that? And the answer is no, for the exact reason I just said, that objects have mass whether they're moving through the Higgs field or
Will
not.
it increase it? I mean,
Uh,
massless objects have like photons if they're moved, or
Massless objects like photons don't even know the Higgs field is there. It's like a neutral object not knowing that there's an electric field there, right?
But
That's
the idea is that if objects are going to move near the speed of light, they're going to be a lot more massive, right? I mean, isn't that?
to us, but of course not to themselves.
Okay, so
Like,
it's not.
yeah, so there is some observer now who thinks you're moving very close to the speed of light, but you obviously don't think you're heavier than you normally are. So,
Okay, and then my second question is, so you mentioned the three big things are time, space, and mass, but what about energy in general? I mean, where does that come from?
yes. So the question is, I mentioned space, time, and mass as the big three, and you said, how about energy? And the truth is, the best definition of mass is that it's a very common form of energy, and it's the most common form of really, really dense energy, right? So it appears to be anomalous, but it's actually, and it perhaps is because it's also the charge of gravity. So it probably is special, but yes, it is just a form of energy. And general relativity is a theory of gravity, but it's also a theory of how energy couples to matter and to itself.
Then, sorry, what about dark energy though? I mean, because the idea is that that's causing matter to move away from each other. So how would that work with the?
Oh, so the question is about dark energy and how that works, and I can answer that very easily. We don't know how dark energy works.
With the Higgs?
Yeah, that would be an excellent PhD thesis for all of you following along at home. Write that down. That's a great topic. So there's a lot about dark energy that we have just begun to touch. Yes, Peter.
So in astronomy, we often also do big projects, but then big project might involve 5 or 10 students, and we have a hard time often finding out what they all can do and still have like a productive thesis and a productive life and a happy outcome. And even when there's 2 students doing the same thing, we sometimes worry, how does that compete, etc. Now, Atlas alone had 1,000 PhD students. So how does that work? What is the sociological aspect?
Yeah, so the question is about the sociology of large experiments. How is it that we can have 1,000 graduate students and know what each is doing and be able to advance their careers by understanding what they do individually? And you said that in astronomy, we really don't like to have a student do, 2 students do the same topic. And that's true in high energy also. There are hundreds and hundreds of interesting things to do within Atlas. Rarely do we have students doing exactly the same thing. So I showed you sort of what are called the cut and count. There's other people who are doing this with neural nets. There are people looking in the various decay modes. There are people who wrote a thesis on the first part of the data and now postdocs. So you can divide it up many ways and have individual ownership of work and ideas and so on. What we have to do is rely on letters of recommendation, because you can't just point to a publication list, because as Tom pointed out to me, I have 850 publications, and that's an embarrassing number.
How many authors per?
Yes, the papers per author, I'm pretty low. So when Atlas publishes a paper, we have of order, is it about 2,000 names signing it? So on many of those papers, I only own like 1/2,000th of the paper, so it all works out. Yes.
This is another sociological question. So there are all these different experiments going, postdocs working and predocs working in 2 different experiments. At some point, the decision is made to make the announcement. And then remember, I have a future son-in-law who works there. I'm being there a couple days. How do they make the decision when to make that announcement?
So the question is, how do we know what sets our schedule, basically? Why is it we made an announcement at a certain time? So there are certain high energy physics is highly ritualized. We have these conventions and conferences every year, and you go there and pay homage and stuff. So our schedule revolves around these conferences. So then the accelerator sets its schedule around these conferences, and so then the accelerator, when they give us the data, is set so that we have a big slug of data right before these conferences and can analyze it. And so it's sort of self-fulfilling prophecy that we get big results before big conferences because that's how we've designed it. And why these conferences happen to be the lucky ones, it gets kind of crazy, but that's basically what's going on. And we try to give data, and lots of big conferences come and go without major discoveries. It's when you get that big slug of data before an important conference and everybody's ready. Catherine.
I had a really general humanist question, and that's if you have a Newtonian worldview of sort of a view that measurements can be observed and reliable laws by which the world can be understood, and then you have an Einsteinian worldview of perspective, what would the Higgs Bosonian worldview be? The philosophical implications of
that's very interesting.
these experiments.
That's so the question was, Newton gave us a certain way of looking at the world, sort of the classical, the world is a well-made clock, and then Einstein sort of brought in relativity, and that it depends on your perspective. So what philosophy would be informed by the Higgs? That is really an excellent question. Let me know when you get an answer. I'm sure it's just short-sightedness on my part, not being able to come up with something. But maybe in 50 years it'll be obvious, and people will laugh at me for not knowing the answer. But I don't. It's sort of the quantum view, I guess. But
Do any of the other physicists in the room have an answer?
I think you said it, the quantum world, right?
yeah, the quantum world, that things are understood statistically, but in the high statistic limits, you get back what Einstein and Newton would have predicted. And so it's a radical departure. We can't tell where each electron is going. In fact, the electron doesn't even have a position until you measure it. So that's sort of crazy making in a different way than Einstein was crazy making. But in the end of the day, you make measurements and compare it to theory, and it's all good.
These are great questions. Let's have two more. So, Paul, you can.
Yes.
Go back to your sociology question.
Okay.
Years ago, the French mathematics community dealt with these 2,000 authors by having Bourbaki, which was a publisher. Why don't the physicists do that?
So the question is, why don't we solve this issue of big authors the way the French mathematicians, big groups of authors the way the French mathematicians did? And I would say that getting all those French mathematicians to make a decision is anomalous. I mean, for us to be able to get it in a room and make a decision, I've actually been in the room where we tried to do things differently. Let's just have first author be the graduate student, but then which grad? If there were two graduate students, they contributed, so it just gets messy. And again, it's sort of this is our best worst idea, right? It's our best bad idea. And the astronomers do it differently and perhaps better. They do get together to do these big projects, but then when they publish in small groups. In high energy, we do our work in small groups, but then everybody is on it. That's why I have 850 publications. In truth, I'm only doing 2 or 3 serious publications a year with my group, and those really count, and those are the ones I highlight, and so on. But yeah, we're stuck with this system, unfortunately. Yes, blue turtleneck. Oh, I'm sorry. No. We got to go with the yes.
I was wondering what you think about all the public attention to the experiments and the Higgs in general. If you're surprised in any way, if you think it's distortive in any way, what your take is on that.
So the question was I surprised, or was I surprised about the level of attention, and did I feel like it was perhaps bad? That's also a very good question. I was surprised. I mean, I was involved in a fairly big discovery in 1994 at Fermilab, and that was a big deal, and I was really at the center of it. And, it was huge. There were lots of articles, and I thought it was great. This is so much bigger, and I had no idea it would be so much bigger. And so I was surprised. And do I think it's bad? I mean, you paid for it. Don't read the newspapers if you don't want. Don't go to the movie, right? You paid to go to this movie. You paid to make this movie, but you don't have to go to it. So you can ignore it. I thought it was good. I thought, there were aspects that were bad, like always harking back to the God particle, which, you know, is flamboyant. You know, that was invented to sell books, and it did, but it hasn't served us well. And so that's probably the only aspect of this that has been negative. No, I think it's good for science. I think it's good.
Can you borrow the mic here? We're sharing one mic here. So let me, on behalf of the entire group, thank Paul for this lovely talk that really got us up to speed on